red, right? Yeah. Give yourself some room. Don't write anything right next to the oxygen red. Go over here to the center of the page and write down for the oxidation, just write down what you started with and what it oxidizes to. It was Br negative, and you're going to do the thing that oxidizes over here. The thing that reduces is you have to include the entire term. Don't put Mn plus 7. You have to include the entire term that it's in. It's in the form of MnO4 negative going to Mn plus 2. It is super important to include the charges on all of your ions. Don't leave the charges off. Because when we go to balancing the charge with the electrons, you have to have the charges in. Yes?
Sorry. Is it really necessary? Like, do we have to write the state of like what the ion is? I mean, like the compound or the molecule, or whatever, like aqueous or liquid. Or...
The physical state? No. Nope. Don't worry about that. I suggest in my Chem 1 class, I make the same suggestion here. If you have different colors of pens or pencils, this is something that I found to be very helpful, using different colors for the different steps. When you look back at it, if you look back at it, the different colors will kind of help you to conceptualize what you're doing each step. So if it's convenient for you to use different colors, then do that. It's very convenient for me. I've got 4 colors up here. And so you'll see me doing that. I do that with all the redox balancing that I do, just to contrast the different steps. So what we've just done is step 1. That was writing the 2-half reaction. Step 2, we're going to balance all the non-H and O elements. And in the oxidation half, with a different color, I've got 1 Br on the left and 2 Brs on the right. So there it is. I do need my 2 in front of the Br. But that's going to wind up changing, you'll see. Then the oxidation half, I can't do much else with. The reduction half, I got 1 Mn and 1 Mn, so I don't do anything with that. They're already balanced. Now the oxygens are not balanced, but it says step 2, do all the non-H and O elements first. Step 3, we're going to balance the oxygens with water. So if I have 4 oxygens on the left, I need 4 oxygens on the right, but it's in the form of water. Yeah. Now I keep these 2 steps in the same color because they go together so much. I didn't have to worry about the oxygens or hydrogens in this half reaction because there aren't any. But there were oxygens here, so I need to account for the oxygens. And that means I have 8 hydrogens that I've finished with. I need to have started with 8 hydrogens. Because it was an acid solution, I can pull 8 hydrogens out of the solution. Everybody okay with that so far? So it's kind of strange. We've never had to do this before, if you hadn't seen it before, adding waters and hydrogen ions to an equation that seemingly didn't have any of that. But because it's aqueous, because it's an acid, there are those other things that are present in the environment that can be used by the reaction. So we now have done steps 2, 3, and 4. It does go pretty fast, especially when you get the hang of this, and you can just zip through this. It's real nice. Both are balanced for the atoms. Next thing, yes?
Why do we add like hydrogen?
Well, the oxygen came first. We had 4 oxygens here, so we need 4 oxygens over there, so you had 4 water molecules. That introduced the hydrogen ions, so now we have to come back, and if there's 8 hydrogens at the end, we must have had 8 hydrogens at the beginning. Okay, so do the oxygens first with the water, and then take care of the hydrogens after that. The next thing is balancing the charges. I think we're on step 5.
Yeah.
Balance the charges. And I told you in parentheses on that step. In the oxidation half, remember, oxidation is the loss of electrons. So, a different color, I'm going to add electrons to the products. This oxidation is losing electrons. It will every single time. The electrons are going to go in the products of the oxidation. They're always going to go in the reactants of the reduction, because reduction is the gain of electrons. How many electrons are going to be lost in this oxidation? Well, just look at what the charges are. I've got 2 negative 1s here, so I've got a total of -2 on the left. This thing is neutral. So if I have a -2, how many electrons would I have to add to make the charges balanced out?
2.
2 electrons. Now, keep in mind that the charges don't have to be neutral on both sides. They just have to be the same. They don't have to be neutral on both sides, just the same. So I've got -2 over here, I add 2 electrons, -2 over there. Cool. For the reduction half, I know I'm going to have to add electrons to the left side, because reduction is the gain of electrons. Over here, that's neutral. My charge is +2 on the right. Over here, on the left, my charge is +8 and -1, +7. So I have a +7 over here and a +2 on this side. How many electrons would I have to add to this side? 5. Right. So if I add 5 electrons, now my +7 becomes +2, and that is what balances that. That's how we do the electrons. Once we have the number of electrons, now both half reactions are balanced for atoms and for charge. So they're good. However, I can't add them back together yet until, if you can imagine this, I can't have a reaction that gives off 2 electrons in one part, but then takes in 5. If I'm going to give off 2, I should be taking in 2. So the number that the number of electrons given off in the oxidation must equal the number taken in the reduction. Hey guys. I was thinking, sorry, I'm thinking you were from last hour. I'm like, okay, what's up? It's good. Good to have you back. So the next thing that we have to do is to kind of scale the reaction so that the number of electrons given off equals the number taken in. This is step 6. This is where we have to use a multiple, a common multiple. What's the lowest common multiple between 2 and 5? It's 10. So we're going to have to try to get 10 electrons given off and 10 electrons taken in. That means, my original color was red. That means that I'm going to have to take this whole thing and multiply through by 5. So getting these electrons to equal out is at the expense of everything in the whole equation. I have to multiply the entire reduction through by 2. And that's going to get me 10 electrons. Everything else just gets whatever coefficient they get. So let's see, I'll just rewrite the oxidation and reduction. Multiplying through the oxidation by 5. It's going to be 10 bromides, or not plus, yields 5 Br2s and 10 electrons. In the reduction half reaction, multiplying that thing through by 2, 10 electrons. 2 times 8 is 16 hydrogens. And 2 times 1 permanganate. Remember, keep those charges still in there. And then on the right side, 2 Mn plus 2s and 8 waters. Now that I have my electrons equal on the left and on the right, I can go ahead and add these together. Anytime you add the oxidation and the reduction together, if there's anything that's on both sides, you can either reduce or cancel. I did something wrong. Isha?
That's read 2.
Thank you. Megan, is that you too? Thank you guys. There it is, okay. Everything else is good? Thanks. So, as I was saying, everything that's on the left and on the right, or anything that's common to the left and the right, either you can cancel them, like in this case, those and those, you'd have 10 electrons on both sides, just cancel them out. There's a lot of reactions where you'll have hydrogen ions or water on both sides. Just reduce. If I have 10 on one side and 5 on the other, reduce both sides by 5. So it'll be gone from the 1, and then the other side will have the lower number. You'll see other examples that when we do our first example tomorrow, it'll have that kind of thing where we have to reduce. And at this point, now we had to get the electrons equal to each other so they would cancel out. And now we can just add our reactions back, our half reactions back together to make a whole one. So everything on the left side, there's 10 Br negatives, and 16 hydrogen ions, and 2 permanganates. That's all that's on the left. Yields 5 Br2s and 2 Mns with a positive 2 and 8 waters. So this is now our balanced equation. Before you get excited and do high fives though, let's make sure, and I always recommend this, don't just stop there and assume that you're right. Check it. Make sure that it's balanced for atoms and for charge. If you've made any mistake along the way, like the one mistake that I made, I would have caught it down here. I wouldn't even have known. If I would have forgotten my 2 there, I'd be all so happy and thinking I'm great. But it turns out I'm not so great because I have it wrong. So check. 10 Brs on the left, 10 on the right, 5 times 2. 16 H's on the left, 8 times 2, 16 H's on the right. 2 Mns, 2 Mns, and 8 O's, 8 O's. Okay, so this thing is balanced for atoms. What about for charge? Negative 10 for here, positive 16, and then it's going to get positive 6. And then 2 negatives makes a positive 4 on the left. That's neutral, that's a positive 4. So this thing is now balanced for both atoms and charge. Now we feel pretty good that, that we've got it balanced. Any questions about that? Did I leave anybody wondering? Now, I don't expect you to just see this and do a zillion redox problems. We'll start with this tomorrow. We'll do a couple other examples. We'll see what it's like when you're in a basic environment. The entire hour tomorrow is just dedicated to balancing redox equations. Now, on the Schoology page for this class, in Chapter 4's folder, I have a worksheet, a redox worksheet that has 14 redox balancing problems on it. Do those. The answer key is on it. It's part of the document. On the quiz in this chapter, one of those balancing exercises is going to be on the quiz. Yep.
No, what? Have the exact same one. We just changed the numbers.
I can't change the numbers on a balancing exercise, so it'll be the same.
Oh, we're the same. Okay.
Yeah, yeah. So anyway, do those, and do them soon. Not tonight, maybe. Tonight you can work on the acid-base exercises if you haven't gotten to all those. But after tomorrow, when we've done this, yeah, get going on those redox balancing exercises. And at this point, now we have about a half hour or so left in class. You go ahead and work on your lab. Let me know. Oh, a couple things about the lab. And you guys that are watching from your computer, it's too late because you probably have already turned your lab in by the time you watch this.
Oh, you suck, Jeffrey.
You're just cheering for him, Girish. All right, so anyway, just a couple of things that I want you to know. The particle drawing. You only have to do a particle drawing for the unknown acid reacting with the hydroxide. Sorry, I didn't tell you that before. If you've done one with KHP, then just don't erase it or don't change it or anything. I'm not checking it though. I am very closely checking your weak acid titration particle drawing, your unknown acid. Another thing is, anytime you use a burette to measure the volume of something or dispense a liquid, your data table should say what the initial volume and the final volume and the change in volume, all in the data table. I don't need to see you subtracting the 2 volumes in the calculation section. That's not really... Ellen?
Okay, so I kind of did my table, right? Can I just like put an addition? Like,
Yes, that's fine.
Oh yeah,
That's fine.
So,
Make sure that your sections are in order.
wait.
I think that's it. Yeah.
If you don't have space, like you just add it like somewhere else. I don't like point an arrow or something like that.
Don't have space for what?
Like to add like the initial burette stuff.
Oh, in your data table?
Yeah.
Yeah, try to, if you can squeeze it in, just squeeze it in.
Okay.
And just, because I'll understand now, you've already done it, and some people are going to have to do something. If you can try to just squeeze it in there, I'm going to be fine with it.
Okay.
Okay? And in the future, just remember that,
Yeah.
and do it for the, yeah.
My procedure, do I have to like explain what titration is and I just say titrate?
No, don't explain how you do a titration, just say titrate. Yeah, titrate to a phenolphthalein endpoint.
and
Yeah,
do we
here, we
like
ball
just
in.
say
Alright, let's work
standardized
on
goals,
this.
right?
We gotta add to our agreement.
Do you just add one X on both sides of the drawing?